So now we're going to get into a discussion of the atom, the most fundamental particle of matter that one can find. So let's define what we mean by this term. An atom is the smallest particle of an element that can exist. And here's another definition. It is the smallest unit of an element that can enter into a chemical reaction, right? So basically, the atom is the smallest particle that you can find for a particular element. So if you take, for example, an element like sodium, then if you were able to break down sodium into its smallest fragment, then that would be the atom of sodium. So this is what we'll be talking about in this section. Now, even though the atom is small, believe it or not, there are even smaller fragments that are located within the atom, and we'll be talking about what we call subatomic particles, right? So just to give an idea as to how small a particle an atom is, let's take the hydrogen atom. Now, this dot here is about 1 millimeter in diameter, right? So if you take a collection of hydrogen atoms and line them up along the diameter of this dot, it will take about 10 million hydrogen atoms to form that line across the diameter of that dot. So that gives you an idea as to how small the hydrogen atom is. And even as small as it is, there are even smaller particles that are located within the hydrogen atoms. And as I said before, they're called the subatomic particles. So what we'll be looking at here is basically the nature and the type of subatomic particles that one can find within an atom. And there are three main particles. The protons and the neutrons are two types, which are located in the center of the atom. And that center is called the nucleus, right? So we have the protons and neutrons located within the nucleus, while the electrons are dispersed around the nucleus, right? And in terms of the nature and where they're located, that is summarized here in this table, where the proton, let's start off with that. It has a relative mass of 1 unit, and the charge on that particle is +1. And as we said before, it's located inside the nucleus. The neutron weighs about the same as that of the proton, but the difference is that the charge is 0 compared to the +1 for the proton. And as we said before, the neutron is also located inside the nucleus. And then we have the electrons, right? Now, the electrons, as you can see here, its mass is much less than that of either the protons or neutrons. In fact, the mass of the electron is about 1 over 1800 times that of either of these two particles. In terms of the charge carried by the electron is -1, and it is located outside the nucleus. So as stated here, the electrons are dispersed around the nucleus. All right, so that's basically how these charges, or I should say how these particles are and their nature and where they're located. Now, let's talk about the periodic table. In fact, let me see something here, because I think I introduced the periodic table to you. Let me just go back up a few slides here to show you this. If you remember, we talked about the arrangement of the elements in the periodic table, right? So what we're talking about here is this special arrangement here, and that's what we're going to get into a little bit in relation to who first came up with this idea of coming up with a table of all the known elements. And the one that is oftentimes credited for doing this, is this guy, Dmitry Mendeleev, a Russian scientist, and he came up with his version of the periodic table back in 1869, right? And I won't go through exactly what he did, but basically he arranged the elements in terms of some certain properties that were known back then. And then that table, of course, back then did not include all the elements that we know about now, because some elements were discovered since then. So the original table that Mendeleev came up with has undergone certain changes and modifications to end up with the current table that we have today. Now, in the table, each element has a symbol, right, placed in its position inside of a box, such as what you see here. And then there's a number that is given for each element. That's the atomic number, which by definition is the number of protons in the atom of the element. So each element has its own unique atomic number. So for example, nitrogen here is the only element which has an atomic number of 7. And that 7 represents the number of protons that is present in the atom of nitrogen. All right? So different elements have their own unique atomic number. Nitrogen is 7, sodium is 11, neon is 10, and so on and so forth. Now, another term that I need to talk about here is what is known as isotopes, right? Isotopes are basically atoms that have the same number of protons but different number of neutrons, right? So any atom or atoms that share the same number of protons but the number of neutrons are different, they're known as isotopes, right? Now, the atomic number we talked about before, and remember we said that by definition that's the number of protons in the nucleus of a given atom of a given element. And as such, each element has its own unique atomic number. But there's another number that's associated with each element, and that's called the mass number. Now, the mass number is not as unique as the atomic number, right? Because as you're going to see in the definition, the mass number is the sum of the number of protons and neutrons present in the atom, right? So whereas the atomic number is unique, the mass number is not unique for a particular element. In other words, you can have two atoms of the same element having different mass numbers, right? And the elements that have different mass numbers would have different numbers of neutrons, and therefore they're isotopes, right? Now, we can determine the number of neutrons based on the difference between the mass number and the atomic number. So as stated here, the number of neutrons would be equal to the mass number A minus the atomic number Z, and that's basically it. That's how you get the particular number of neutrons for a particular isotope. Okay, so this here is basically a shorthand way of representing an element along with its atomic number and mass number. So E here, in fact, let me write this down. E represents the symbol of the element. So this here would be the element symbol. A here would represent the mass number, and Z here would represent the atomic number. Okay? That's Z, all right? So all this combination here, we call this the isotopic symbol. Isotopic symbol for a particular isotope, right? So in this particular case, this is the isotopic symbol for a particular isotope of chlorine, right? So as we said before, it's kind of partially blocked here by what I wrote. The atomic number is, again, by definition, the number of protons present in the nucleus of an atom of a given element, and the mass number is the sum of the number of protons and neutrons present in the atom of a particular isotope. All right? And the number of neutrons is, so this is just repeating what we said before. The number of neutrons will be the difference between the atomic number and the mass number. All right? Okay, so let's look at this example where we have two different isotopes of chlorine, right? So as you can see here, they both have the same atomic number, which means that they're both isotopes of the same element, but the mass numbers are different, and that's the reason why they're isotopes. So based on this information here, you should be able to answer these questions. The first question of which is, how many protons are in the chlorine 35 isotope? And the answer would be 17. And the next question is, how many protons are in the chlorine 37 isotope? And the answer again would be 17. Now, in this case here, the question is asking how many neutrons. And the answer would be 37, which is the mass number in the case of chlorine 37, minus 17. And that works out to be equal to 20. So in the chlorine 37 isotope, the number of neutrons would be 20. All right, so that's a relatively simple example which illustrates all the different terms that we just learned. We just learned about isotopes and the relationship between the mass number, the atomic number, the number of protons, the number of neutrons, and the number of electrons. Okay, so based on what we have just talked about, we should be able to answer this question here. So this question is asking how many protons, neutrons, and electrons are present in a bromine 81 atom. All right. Now, in this case, they did not indicate obviously or clearly the atomic number. So you can look that up in the periodic table, because remember, each element has its own unique atomic number. So if you go to the periodic table and look up the atomic number of bromine, you'll see that the atomic number is equal to 35. All right? So basically, we have the mass number, we have the atomic number, so therefore we can determine that the number of protons is equal to 35. All right? Now, in an atom, the number of protons and the number of electrons would be the same. And we're going to talk more about that, I believe, in a subsequent chapter. But in a neutral atom, the number of protons and the number of electrons would be the same. So in this case, that would be 35. So now we get to the number of neutrons. The number of neutrons, in this case, would be equal to the mass number, which is 81, minus the number of protons, or the atomic number, which is 35. And when we do that calculation, 81 minus 35, the answer works out to be equal to 46. So the number of neutrons in the case of this particular isotope of bromine is 46. Okay, so that's basically all that we have to say for now with respect to atoms and the different particles that make up atoms. Okay, so we're going to stop here, and the next topic we're going to talk about is compounds. All right, so until next time.